square. So that is interesting. So let's look at this example problem in the text and how to use this tool to analyze the dynamic problem of interest. Okay. I have wall, which is again interesting wall, and the bottom that has no friction. And I have pallet, and then I have a spring over here. And I suppose I am moving this mass by pressing this one by the length of air, and then release. Then what will happen? This will move over here with a velocity of, what is the velocity? What is the velocity? Because with the problem we have interest is associated with the velocity and the distance. Okay, velocity, and the distance. What kind of principle we would like to use? If the variable involves in velocity and distance, work done concept is useful because work done involves force, displacement, and velocity. We don't have to use Newton's second law. Okay? Now, then the terminal velocity when this mass over here would be obtained by applying work done in this change of kinetic energy. Work done in this case is what? Because we are handling the spring force that is conservative, therefore I can write over here this work done should be V1 minus V2, and the change of kinetic energy is T2 minus T1, and initially this is 0, right? And initially V1 is 0. No? Okay, V1 is when I compress this. That's the state 1. Right? When I compress that, only there is potential energy. When I release, this is state 2. There's no potential energy because the mass is already, mass left the spring already, right? So V2 is equal 0. And T2 is not 0. Therefore, I can write 1/2 K L square has to be equal to 1/2 mV2 square. This is the equation I obtained. Okay, right? And then, as drawn in the text, it follows the hoop. Okay? And the example asked us to get the minimum L that allow this particle move around. What it means, it has to contact the roof when it passes over here. Okay, if the velocity is very large, then this particle will push the hoop. Okay? To see what happened, let's draw Newton's let's draw a free body diagram when it is over there, and call this is state 3. Okay, then the free body diagram says there is a mass, and due to the presence of gravitational force field, that is mg. Okay, and there will be some force acting this direction, normal direction, which means that the mass is pushing the hoop, and that has to be equal to MAT, tangential acceleration. I'm applying Newton's second law. Okay? And what is it? Normal force. Is it this direction or that direction? Because AT is moving that, so therefore this is unit vector, and then this is another unit vector. So direction would be this direction, right? So that has to be this direction. Whenever you confuse with the direction of normal acceleration, you always do this. All right? This is ET. And when it goes there, that is ET prime. Therefore, the direction has to be this direction. Okay? And then you can write, hey, this is equal to m v3 square over radius of r. I say this is r. So I can write that mg minus n has to be equal m v3 square over r. So number of equations that we have is 1 and 2. We do know v2 square is this. Okay? And we want to estimate the L. Okay? What is the work done from this state to that state? Because there is no friction, energy would be conserved. Therefore, this energy will convert it to two terms. One is increase of potential energy. Another one is kinetic energy. Right? So we have 3 equations. 1, 2, 3 equations. How many unknowns we have? We do not know. We want to calculate the L, and we do not know V2. We do not know V3, and we do not know N. So we need one condition or constraint that provide us additional equation. What would be? The condition in the text example says the minimum L that allow this particle contact with the hoop. What it means? N can be very large, or N can be very small. If it has just the contact, that means an approach to 0. So we have another constraint. So that allows that approach to 0. Therefore, we have 3 equations and 3 unknowns. Therefore, we can estimate the minimum length L. The spring has to be compressed. Okay? So let's review this result. This is interesting. We apply principle of work done. We apply conservation of energy. We also use Newton's second law to get the solution. And you have to note that each principle has its own property. Newton principle of work done involves only velocity displacement, not acceleration, right? Therefore, it means that if you use principle of work done and kinetic energy, you have a very strong slipping energy now. So if you have to select the principle according to the dynamic property of the system as. In other words, if it involves velocity and displacement, it suggests to you to use principle of work done and kinetic energy. If the dynamic system you're handles acceleration and force, it suggests to you to select Newton's second law, right? So I said I gave you two tools. One is Newton's second law, the other one is principle of work done. Okay, now let's move another way to see the dynamic problem, which is principle of impulse and momentum. Okay, we always start with the Newton's second law. Remember, we start with the Newton's second law when we get an expression of work done is equal to change of kinetic energy, right? So start with Newton's second law, that is force induced change of momentum. That means physically, it means if I apply force with some time, this will induce change of momentum mathematically. Right? I just to change the mathematical expression of Newton's second law. That means if I apply the force on this body for certain time, it will change the momentum. That is interesting. The other way to look at the dynamic system. So that means if I integrate mathematically f dt, this is still vector. This will induce change of dmv that I can write from 1 to 2 mv2 vector minus mv1 vector. All right? And this is a linear momentum, so I can write it as L2 minus L1. Or I can write L1 plus integral f dt is equal to L2. Those are vectors. This is a principle of impulse and momentum. Okay? Graphically it means let me ask you, what is the impulse? in this case. What I'm saying, impulse in this case, integration f dt from 1 to here, 2. That I call this is impulse. Later on, we will talk about impact.